We're going to talk a little bit about the structure of atoms and how we describe what's going on in an atom and with the periodic table. All right. Anybody know the story of atoms? Where they first came from, or why we think there are atoms? Have you ever heard this before? I'm not going to go in great detail into it. Your book does. It kind of goes through all the classic experiments to discover the different parts of the atom. That's great. It's super interesting. If you are interested in that, I encourage you to look at it. But I'll just give you a quick background. The idea of atomic theory is that matter can be reduced down to these small things called atoms that give it some sort of inherent identity. So something made out of a particular atom is going to be different than something made out of a different atom. We kind of talked about that when we talked about elements versus compounds. So that was actually a fairly revolutionary theory at the time. We're talking about in the 1800s, because before that, it was thought that different materials had different kind of bulk intrinsic properties. And the idea that a material made from nitrogen and oxygen could be different from another material made from nitrogen and oxygen was not really thought of as possible or in that way. So now we know that that's not really crazy, that that's actually true, that you can have these atoms combining together in these different ways and making different stuff. So that leads us to this periodic table. We've all been staring at this for a few weeks now. We haven't really thought about what it means or what's important about the various ways it's laid out. It's kind of an unusual shape, has these kinds of sections to it. Does anybody know anything about the periodic table? Why are things arranged in some of the sections that they are? Why does it have the shape it is? Why is it called a periodic table? What about it is periodic? Anybody know any of that stuff? Have you thought about that before?
Doesn't it go from like most effective to least effective?
Most effective to least effective? Well, I'm not sure exactly if effective is the right description, but you're right that it goes from one kind of, it like trends from one thing to another as we go across, right? We'll talk about some of those trends too.
So kind of like what they're made up of, from like protons, neutrons, and electrons. And then they're grouped into like metals and stuff.
Yeah, so some of it tells us a little bit more. Yeah, like what you said, that we can group them into some metals and some other things. What were you gonna say?
How many protons?
Yeah, right. Something about these particles that actually make up the atoms. Where does this word periodic come from? Why is it called the periodic table? What does it mean for something to have a period?
An end.
We put it at the end, like the punctuation. This is actually a different. I'm not sure how that punctuation mark got its name. This refers to a different kind of periodic that has to do with a cycle. Usually if something is periodic, it means it kind of repeats over and over again in a cycle. We can talk about a wave being periodic. We can talk about seasons being periodic, a year or something like that. And the table is actually the same way. Even though it's written across kind of just on the wall like that, the way it works is as we go from left to right, we find along a particular row, we find kind of different things happening. Like lithium's like this, beryllium's like this, then we go to B and C, and every one of those is different. And we get to Ne, neon, down number 10. And then we start over and we go to 11 over here, and Na, sodium, is acting a lot like Li, lithium. And then Mg, magnesium, acts a lot like Be, beryllium. And then Al, aluminum, acts like the one above it. So it's like we keep seeing the repetition of these properties. So across the rows of the table are called periods, because every time we get to a particular spot, it seems to have some similar properties to the last time we were at that spot. And that's what's periodic about it. Because of that also, the columns going up and down are called groups, and that they have some similar properties. So those groups will have some similar properties in terms of how they react chemically, how they look, things like that. So I will grab this one picture from the book here, and we'll look at a couple of parts of the periodic table, a couple of things that you should know about it. So this is coming.
Do you have to learn by heart?
No, you don't have to learn this by heart. We will always have the little portable periodic tables that have the names on the other side. So there's our periodic table. Now we can write on it a little bit. And we've got a little more information here than we have up there in that it's kind of color-coded. The importance of those color codes are down here. And we separate this into basically two parts, the metals and the non-metals. And you'll notice that the separation line is this black staircase kind of thing that goes right down here. You see that on that one as well. The elements that are right on that staircase are called metalloids. Do you know what that oid means? If something is like something oid? It means kind of like. So it's not a metal, it's a metalloid, which means kind of like a metal. Another word for that is a semi-metal. Like android, an android is kind of like a person. Yeah, that's what that means. Or humanoid, it's like an alien that's kind of like a human. That's what that means. So you've got your metals, you've got your non-metals, and then the kind of in-betweens in the middle. What is the difference between a metal and a non-metal? What's special about metals? How would we tell a metal from a non-metal in a physical way? Has anybody here seen metal before? Hopefully, maybe. So it's solid, but non-metals can be solid too, right? And actually metals can be liquid, like mercury. So what else?
They can repel.
That's magnets, and some metals are magnetic, that's true. But some non-metals have magnetic properties also.
They have specific structure from protons and electrons inside.
That's actually true.
It's called,
Yeah. Okay, I'm not sure exactly where you are with that, but all atoms have that structure. But you're right that metals have a little bit different atomic structure, or a little bit different way that the atoms kind of pack together. But it's not that different.
The state of the metal.
Okay.
It's
What about how they look? So let's think about metals. Think about the metals that you know, that you've seen. Gold, silver, copper, zinc, iron, steel. What?
they're solid.
They're solid. How would those compare how they look to something like sodium chloride, table salt, or... So what makes something metallic? Shiny, yeah, shiny and reflective. That's actually a really important property of metals. Shiny, reflective. The official term is lustrous. They have luster, which is this way of reflecting light. And that's true of all the metals. Some of them are shinier than others, but they all have that. Even something like mercury that's a liquid is shiny, it has that shininess. Other things that we see in metals that we don't see in non-metals. They are conductive, they conduct electricity, which means if you try to pass an electric current through it, it will pass easily with very little resistance. We know that as like wires being made out of metal and that kind of thing. And then there's another set of properties we say that they are malleable and ductile. And this has to do with what you can do to them. Has anybody ever heard those terms before? A little bit. What does malleable mean?
You can mold it, shape it.
Yeah, you can shape it. If you take iron and you hit it with a hammer, or like, go up to your car later and just smash the side of it with a hammer, assuming it's a metal car. Don't actually do that. I mean, it's your car. You can do that if you want. But what happens to it? Does it just shatter and fall to the ground? No, what happens? It dents, right? It dents. So metal, you can shape and you can hit, and you can actually, if you took a piece of metal, you could hammer it out until it became a very thin sheet and it wouldn't break. If you did it carefully, it wouldn't break. So that's called malleable. And ductile is kind of like that. It means that you can pull it into thin wires, that it can be kind of melted and stretched out into these thin wires. That's not something you can do. That is something you can do with some non-metals, but in general, that's a different kind of a property. So those are properties that are unique to metals. And you could even try the malleable thing with, if you have aluminum foil, and you know how like after you use aluminum foil, it's all kind of crinkled up and bent up. If you put it down on a surface and you smooth it out with a lot of force, like with the back of your fingernail or with a credit card or something, you can actually get it to smooth out, so there's no more wrinkles in it at all. And that's because you're really actually pushing those atoms around and changing the shape and thinning out that aluminum foil. It'll be thinner after you do that. That's that malleability. So the nonmetals don't have that. The nonmetals will see a lot of gases. We'll see kind of brittle kind of materials. That's how we would describe sodium chloride, rocks, things that when you hit, they shatter, they break apart into pieces rather than stretching out and forming new shapes. And the nonmetals are also not conductive, electrically non-conductive, meaning if you try to pass current through them, it simply won't. They will do something called insulating. They'll insulate against that electric current. They won't allow the electric current to pass. And then the green ones in the middle, the metalloids, what do you think they do, if you had to guess? Yeah, they are kind of in between. So all of their properties are kind of like one and kind of like the other. For instance, have you heard the term semiconductor? Those are semiconductors, meaning they don't really conduct that well, but they're not really true insulators either. They kind of conduct just okay. Now, as it turns out, that's a really important property, and we can use that to make things like computers, like silicon. Si is a metalloid or a semi-metal, and so that semiconductive property can be used to do all kinds of fancy stuff in electronics, but they're just basically in the middle. So they have some properties of one and some of the other. But that's how we separate in broad categories. We can also talk about some names of some of these groups that have very similar properties. And I know that the words are getting a little small up there, but you'll notice the groups being numbered in a couple different ways. There's two numbering systems. There's the old, what we call the old numbering system, which is what you see up there, the A's and the B's. And then there's a newer numbering system where the groups are just numbered straight across from left to right, 1 to 18. Most periodic tables you see will have both of them because they're still both used in different ways. So like that first column of elements, H through FR, we might call them the group 1A elements, or we might call them the group 1 elements. They also have a special name, the alkali metals. And then the ones next to them have a special name, the alkaline earth metals. This whole big block in the middle, what we sometimes call the B block, is known as the transition elements or the transition metals. And then we've got a couple more names over toward the right. The halogens are the group 7A, and the noble gases are the group 8A. And those terms are still used a lot. So it'd be good to know those. All right, so we're going to start with the ones over on the left. We're not going to talk about all the properties of all these different groups, but I want to give you a sense of what it means for a group to have similar properties. Do you know anything about those elements in group 1 or group 1A? Especially those metals. Do you know anything about them?
They're very reactive.
They're very reactive, that's true. And we're going to watch a short video in a minute that kind of shows that. So they're all very reactive in their metallic state. And that's one thing that they all share and that makes them kind of as a group. If we look at a couple of the elements, you may not have heard of all of them, but things like Na, sodium, and K, potassium. We know Na makes NaCl, which is sodium chloride or table salt. K also makes KCl, which is another kind of salt. You might see it. Both of those ions are important in our bodies. We need sodium and we need the potassium. You might see KCl as a salt substitute. So if you have high sodium, you can actually use KCl instead of NaCl as a salt substitute. And it'll still kind of work the same, but then you won't be getting as much sodium if that's an issue for you. And the other element, the other members of that group also have similar properties. So let me see if I can show this video. We've actually done it before. This is, I think this is the one. I'm going to mute it. We have to watch a little commercial here. We're not going to watch all the way through. This is, I believe, if this is the same one that I used before, this is a compilation of a few different videos showing these reactions of some of these different alkali metals. It should be the alkali metals. So they react with water to form hydroxides, and they make hydrogen gas. As that hydrogen gas gets formed, it's also a very exothermic reaction. We talked about that. What does that mean? Yeah, it produces a lot of heat out. So it makes stuff hot as this happens. And then as we move down the group, they get more and more reactive. So let's see if we can see this. Oh, you know what? I don't have the sound. Let me change my sound output a second. Let's see if it works now. Yeah, still no sound. That's okay, we can watch it. Just imagine it making sound. So you saw, it's not that exciting, but you saw lithium here. I missed it a little bit. You put a little bit in water, and it kind of fizzes around and then kind of lights up on fire because it's forming flammable hydrogen gas and getting hot enough to actually ignite that gas. So then we try it with sodium. A little bit in a beaker of water. Obviously, it would be more fun to just do this, but they don't like when we do these sorts of things in classrooms.
We have goggles.
We do have goggles. We could do something similar in the lab. So you can see, it becomes quite vigorous. And what happens, the reason that it gets more and more, I guess I can let it go like this, like that, these metals also melt at a very low temperature. So they produce enough heat to actually start melting the metal. And when it melts, it goes, little droplets of the metal go down into the water. And here's what happens if they drop a huge chunk of it in a lake. So they throw it down there. Actually, yeah. And you see it kind of producing the steam, starts to light up, and then just goes, right? And then all the little pieces come down and they ignite too. So that's sodium. So you can see just a tiny bit, and he has to sort of run away as all of the water just explodes from this vigorous reaction. Rubidium is even more vigorous. It's hard to tell in that particular video, but that was just a tiny bit.
Is this a how not to do it video too?
Yeah, kind of. So they throw this in a bathtub here, and you can see it kind of blowing out the bathtub. And then you've got cesium, spelled two different ways. Tiny, tiny little droplet of it just blows out that whole thing. So as you might expect, yeah. And francium we don't have, so they try to pretend. Francium is radioactive, and it only actually exists for a few minutes, 20 minutes or something like that, before it breaks down into other stuff. So there is no actual samples, there aren't enough samples of francium that you can really get and do this. But that is a sense of the alkali metals. So now that I've got, I thought I had this thing set up now. Let me see if I can find that sodium one in the lake, because it's, yeah. I don't. It doesn't want to play the sound, so we probably have to restart this or something to get the sound. There we go. No. I think this is the one we just saw, but they threw it in the lake. Let me show you the actual sodium itself first. So sodium is right there. You can see it doesn't really look shiny and lustrous. It looks kind of whitish and chalky, and that's because sodium reacts with water in the air, and it forms a protective coating of sodium oxide around it from the reaction. So to get it to react, what you have to do is you have to actually cut it off, and it's smooth. It's kind of like butter. You can cut it with a butter knife and expose a shiny surface. So I think they are doing. I don't know if they're going to do that, if they just kind of. It's not a good idea to use like power tools on a block of sodium, but let's watch. They throw it in. And you can see nothing really happens for a minute as it just kind of ignites, and then all of a sudden, boom. And it throws little pieces of sodium all around. It isn't toxic or anything, which is why it's not that terrible to do it in a pond. But
So where do we usually use this method?
what?
Where usually do we use them?
Why?
Where?
Oh, where? Well, in their pure metallic form like that, not a whole lot, other than in research applications. One exception is lithium, which is in this same category, has those same kinds of effects, and is used in batteries, like lithium batteries. Those are very high energy batteries, which is why they sometimes have explosion risk. I don't know if you've seen, let's look that up as long as we're watching videos of things exploding. I've seen, yeah, let's see if I can find where this is. So a laptop battery is actually any lithium battery is potentially an explosion risk. The reason is that the lithium inside holds a lot of energy, and you also have some of that lithium metal, which is then explosive, or not necessarily explosive, but reactive with water in the air. So when lithium batteries are allowed to run down too far or overcharge too far, they can explode. And any kind of common laptop or cell phone type battery should have circuitry inside it that prevents it from doing that. But that circuitry can be overridden, or if it breaks or something like that, that could not do that. So here, they actually did this. They sort of forced it to get to that low state. So you can see what would happen to a computer if that lithium battery starts to go. And as these cells start to fail, it becomes kind of a chain reaction. So you can see that little bit of smoke is like one of the little lithium cells failing. And there goes another one, kind of next to it. You can see that smoke coming out. And then, yeah, there it goes. So lithium is used in those sorts of things because of its high energy density. The others are often used in catalysis, that is making things from other things. Yeah, I know it gets a little bit crazy here. But you have to use sodium or potassium or mixtures of the two for various chemical reactions to make whatever you're trying to make. So anyway, this is just going to keep going on fire. Let's see, where does it start to get really good? Oh, now the plastic's burning. So I think it just keeps kind of burning like that now. Yeah, it's just on fire. So that can be a danger of those lithium batteries. But anyway, the point of all those videos, besides that it's fun to watch other people exploding things, is that you can see that all of those elements in that group have similar chemical properties. There is a trend, there is a slight change each time. They get more and more reactive, but the property is similar of reacting with water. If you took some element from another group and threw a big chunk of it in water, wouldn't do that necessarily. So we'll see some of that. So that's part of kind of these periodic trends and this idea of groups and periods. We have a little time left. Let's just go over, I know some of you already described it, but a little bit of the structure of the atom and some terminology that we use in describing the atom. So what's in the middle of the atom? The protons and neutrons, and that's called the nucleus. So you've got your nucleus in the middle of the atoms.
So an atom is smaller than a cell?
Yes.
Okay, good, 'cause
Much, 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 much smaller. Like there are millions and millions and millions of atoms in a cell. Well, pretty much, except that it's made up of protons and neutrons, and then those are actually made up of even littler things that they talk about in physics. So smallest is smallest. But the atom is the smallest thing that makes matter essentially what it is. So the reason that iron is different from sulfur is because of the iron atoms versus the sulfur atoms. And so we say that's what we mean when we say the smallest irreducible part. Not that it's not made up of other things, but those other things don't give it this sort of character of what it is. So we've got this nucleus with protons and neutrons. Protons have a positive charge and neutrons have no charge. And then around the nucleus are what? Yeah. And electrons are sort of all over. The symbol for an electron is E with a little minus. They are not, as previously thought, in orbits. They do not orbit the nucleus like planets. Rather, they just kind of exist in these diffuse clouds. And there must, in a neutral atom, the protons and the electrons must balance each other out. So there must be as many protons as there are electrons in a neutral atom. Now, how can you tell how many protons or electrons there are in a given atom? The atomic number, right? Which number is that on the periodic table? Yeah, it's the blue numbers, the number in the upper right-hand corner. Let's draw ourselves a periodic table symbol here. Let's use carbon. We've got C. And then 6 up there. So that's carbon. This number up here is the atomic number. And that tells us the number of protons in the atom. So an atom with 6 protons will always be called carbon. An atom with 7 protons is always called nitrogen. You change the number of protons, you change the identity of the atom. The number of protons tells us the identity of the atom. It also tells us the amount of electrons in a neutral atom, that is an atom with no charge. So if a neutral carbon atom is there, how many electrons does it have? 6, because it's got 6 protons. So it needs 6 electrons to offset that, so it's 0 overall. And then what is this number down at the bottom?
Mass.
It's a mass number. Yeah, it's an atomic mass, but it's a little bit trickier than that. So let me show you why that is. Which parts of the atom contribute to the mass?
Protons.
Protons and neutrons
No.
and electrons? Yeah, it's true. They all have mass. However, the mass of an electron is so small compared to the mass of a proton or a neutron that we don't really count it in the overall mass because they're so tiny. And this is kind of crazy too. The distance between the nucleus and the closest electrons is about 10,000 times. That is, if the nucleus is this big, the electrons are 10,000 times that away from the nucleus. You think about what that means, like let's say we have a meter here. Let's say the nucleus of an atom is this big across. That means that the electrons will be 10 kilometers away, like 6 miles away, if that were the size of the nucleus. There is a ton of space between the nucleus and the electrons, which means most of all matter is what? Like all matter is mostly nothing. It's all mostly nothing. It's all mostly that space between the electrons and the nucleus. A little bit crazy if you think about it, that most of everything we experience is just nothingness, just space between protons and electrons. So far away are these electrons, and the electrons don't contribute much to the mass. So that we have another number that is related to that called the mass number. But the mass number is just the number of protons plus the number of neutrons, because those are the things that contribute to the mass. The other interesting part of this is that atoms can have different numbers of neutrons and still be the same. So you can have a carbon atom with 6 protons and 6 neutrons, and that's called carbon 12. You can have a carbon atom with 6 protons and 7 neutrons, and that's called carbon 13. And those are written in a couple different ways. We can write like that for carbon 12. So 6 protons and 6 neutrons. Carbon 13 would have 6 protons and 7 neutrons. And that little number denotes the overall mass, the neutrons plus the electrons. Anybody know the word for the relationship between these two things? They're both types of carbon, but with different numbers of neutrons. There's a special word for that. You know what it is?
Isotopes.
Yeah, these are isotopes. Same number of protons, different number of neutrons. And that changes their properties a little bit, changes what they do, how they act. It doesn't change their chemistry a whole lot. So after today, we're not going to talk a whole lot about things in the nucleus, because in chemistry, we mostly care about what's happening in the electrons. But it does make them different. So here's the weird question. If the mass number is the protons plus the neutrons, it has to be made up of whole numbers, right? You can't have a half of a neutron in there. You got to just have whole protons and neutrons. So how come all the mass numbers on the periodic table in red have all these weird decimal places behind them? If carbon is either 12 or 13, how come we look up at the table and it says 12.011? Any ideas?
And how many is it all data?
Yeah, that number is actually an average of the isotopes that we find in the world. So 99% of carbon in the world is carbon 12. But about 1% of it is carbon 13. So if you average those together, you get a little more than 12, so you get 12.011. And that's where those numbers come from. There's a little carbon 14 out there too, which affects that. So those numbers are actually averages. A striking example, if you look at bromine number 35, its atomic mass is 79.904 up there. So you'd think, oh, that's pretty close to 80. So probably the most common isotope of bromine is bromine 80. But actually, there is no bromine 80. It doesn't exist. There's about 50-50 amounts of bromine 79 and bromine 81. So if you average 79 and 81, you get 80. And that's what we see up there. So that's where those numbers come from. The good news is we don't have to really care about that too much, because whenever we have a significant sample of anything, we can assume that all the atoms inside have that mass, because there's always so many atoms that the average is just fine to use. So when we do calculations with atomic masses, we will generally look back up there at those numbers and use those numbers. But you should at least keep in the back of your head that any individual atom will not have that kind of a mass. An individual atom, the mass is the protons and the neutrons added together. All right? Or maybe. Okay, let's talk about the electrons, because that's what's really important to chemistry. In a neutral atom, the number of electrons equals the number of protons. Makes sense. If you've got 10 protons and you want that to be neutral, well, that's 10 positively charged particles. You need 10 negatively charged particles to offset that. So you need 10 and 10 to balance it out. What do we call not neutral atoms? You know? What's a charged atom called? Yeah, negative or positive. There's a name for that.
Ion.
Ion, right. Charged atoms are called ions. And their charge is written in the upper right corner of the symbol. So if we're talking about a sodium ion, if we don't see any symbols, we assume it's neutral. If we put a little plus sign up in the corner, that tells us it's a positively charged ion. Since anything called Na is always going to have 11 protons, how many electrons would we have to have one positive overall? 10, right. If we've got 11 positives and 10 negatives, we're left with +1 left over. And so that's where that plus comes up. So how many protons and electrons would be in a chloride ion? How many protons? 17. You see that on the periodic table from the atomic number? 17 protons. So then how many electrons would we need to have an overall -1 charge? 18, right. So if we've got 17 plus and 18 minus, we've got -1 overall. So this can tell us how many electrons are in various atoms, or the electron to proton ratio based on that charge. All right, we are out of time. We'll come back to this on Thursday. Let's head upstairs. Just have your stuff ready to turn in, the pre-lab for today and the report from last week.